All right, so for this lecture, I highly recommend to have a spare sheet of paper and a pen handy. So I'll say a couple times during the video to pause and to work on something on your own. This will help you practice, and these quick 30-second exercises will definitely help you out, especially, say, hint on an exam in the future. So to start off with this slide, nearly all metals, most ceramics, and a large number of polymers exhibit some form of crystallinity. Crystallinity, or crystalline structures, is a periodic arrangement of atoms in a lattice. So basically, the atoms are sitting in certain positions, and it goes to infinity until, well, either the material ends or there's a grain boundary or something like that. So here are some examples of some different crystal systems and crystal structures. So take like 5 seconds and kind of look through it. Can you identify any of these crystal structures? So as an example, the top right here, this is the FCC crystal structure, or face-centered cubic. And the bottom left, or really this whole bottom row, this is BCC. And then this one up here in the top left is actually the triclinic crystal system. And we'll talk more on the next slide about different crystal systems. And so for crystal structures, we'll mostly be focusing on metals because metals, their alloys, and intermetallic phases, all of these are kind of mixtures of different metal elements. All of these are more likely to crystallize into high symmetry structures compared to ceramic and organic materials. What do I mean by high symmetry? Well, basically the crystal structures are just more symmetric than other ones. Actually, triclinic is the least symmetric crystal structure out there. And because of the high symmetry, it just makes it easier to deal with and to visualize. And you'll see some examples of that in a little bit. And so in the upper right-hand corner, again, this is face-centered cubic. So some common metals that crystallize in this structure are nickel, copper, and aluminum. For BCC, maybe you can name a few already, but off the top of my head, tungsten, chromium, and also iron for certain temperature ranges. So obviously iron is not BCC over all temperature ranges. And so in the top left, going back to the triclinic system, so note that you have these distances A, B, and C, as well as these angles between the different unit cell vectors, gamma, alpha, and beta. And so these together define a given crystal system. And so depending on whether or not these are all equal, or if they're equal to certain angles and distances, that tells you what kind of crystal system you're dealing with. So as an example, here are the 7 unique crystal systems. So each crystal system is defined as a character, they have characteristic symmetry operations, and there's a minimum amount of symmetry for that given system. Now, obviously, there are more crystal structures than just these 7. So again, the 7 just define a minimum amount of crystal symmetry. Inside of each one of these crystal systems, there are many other types of lattices that are available to them. And so I would highly recommend memorizing these 7 crystal systems, because this will help you later on down your career path in visualizing and understanding crystal systems and crystallography much better. And so again, note that these crystal systems are defined only by the unit cell vectors. So that is the angle between the vectors and their magnitudes. And again, that these systems are classified by their symmetry operations. But however, within each crystal system, you may have also heard that there are different types of kind of crystal structures. Oops. And so these are called Bravais lattices. And so basically, Bravais lattices are different crystal structures that fit within these crystal systems. So for example, in the cubic system, The different Bravais lattices are primitive, FCC, face center cubic, and BCC, or body center cubic. And so in the case of cubic, there are 3 different Bravais lattices within them. So each Bravais lattice, well, at least the FCC and BCC, these are more highly symmetric than the primitive case. For tetragonal, there are 2 other Bravais lattices. They are body-centered as well as primitive. For orthorhombic, there are a total of 4 different Bravais lattices associated with it. Monoclinic, there are 2. Triclinic, 1 other Bravais lattice. I don't know why it keeps doing that. For rhombohedral, you again have 1, and hexagonal 1. And so these are the different numbers of Bravais lattices that each crystal system has. And so for today's lecture, we're really going to be focusing on the cubic system. It's the highest symmetry, and it's the easiest to visualize. It's great, for as a teaching aid.